So I should start already.
If you just pause for a few seconds, we'll see the participant count increase and let people enter the room. Great, I think we can get started.
Okay, welcome to this morning session in Quantum Battle. So this is a session with invited talks on numerical and analytic methods. My name is Dieter Bauer and I have the honor to chair this session. And probably meanwhile, all of us know how to pose questions. So if you have questions, please type it in the Q&A box or you just raise your hand. And then we can unmute you or I just read your question as you prefer. So the first speaker is Wilhelm Becker from the Max Born Institute in Berlin. And he will talk about the strong field approximation, strengths and shortcomings. So Wilhelm, please.
Good morning, everybody. My name is Wilhelm Becker. And I will talk about the strong field approximation and try to summarize what has been accomplished and what has not, cannot be, and what might be done in the future. First, I'd like to, how can I get my slides? I would like to acknowledge my co-authors on this talk. Let's see, how do I get my slides here?
So you see the share screen button?
Okay. Well, I am on the share screen, but here we go. Here we went. It's gone again. Okay. Yeah, here we are. So first, I would like to appreciate my co-authors, Jing Chen from Beijing, who spoke yesterday, and Dejan Milošević from Sarajevo. And of course, I would like to thank Carla for the invitation and Andrew Maxwell and Andrew Brown for the perfect organization. Everything that does not go well, like I had problems right now, is not their fault. When I received the invitation from Carla, I pondered a while what I should make of this battle. And so I consulted my favorite philosopher, Heraclit of Ephesus, and the statements of his that have been preserved are few and are opaque. And one of his most best known statements is that a battle is the father of everything. I always had misgivings about this. I mean, this statement has been used and abused by the military for millennia, but now I know what he meant to say. It's exactly what we are experiencing here. Okay, this is what I want to do. And when I say SFA, I mean it in the very traditional sense, namely the Born series in the electron-ion interaction. No improvements, nothing else, just the Born series. And okay, here we go. It's very quickly derived. You start from the ionization amplitude, which incorporates the electron time evolution operator in the presence of both the binding potential and the external laser field. Now, of course, we don't know that. So in order to get a series, we just use the Dyson equation here and iterate it. And that yields the strong field approximation. And normally, one only considers the first two terms. The zeroth order term here is what's often called the direct term, or it describes the direct electrons, which means that the electron, after it has been liberated, doesn't see the binding potential anymore. There is a certain conflict here on the use of this word direct, and I'll come to that later. The next order term describes the 1-3 scattered electrons. Here's a binding potential. And so this allows for one and only one interaction of the liberated electron with the core. And then you can keep going. So here would be the second order term, 2 interactions, etc. This actually was written down for the first time by Howard Rees in his seminal ADI paper of 1980. There are limitations of the SFA. Actually, there are very few in principle because the series I wrote down is exact. So if you can sum it, you have an exact solution of the problem. One limitation is that we approximate the final state, which should be a continuum state with a binding potential, by a plane wave, a Volkov wave. Now, if you were able to sum the series, then the initial bound state would get dressed, and also excited bound states would appear in the picture. But we don't do that, we cannot do it, so these are limitations. The possible improvement is a low frequency approximation, which essentially replaces in the matrix element the potential by the corresponding complete T matrix, but without the field. So it's still an approximation. It's a series, so there is a problem of convergence, and I'll come to that later. Now, obviously the SFA is better, the lesser the role of the potential is. So it's ideal for a negative ion, and actually it was conceived originally for a negative ion, weakly bound electron. And I show you a comparison here of, this is ionization of fluorine, the negative ion. And here's an SFA calculation, only the direct term. And here's an exact solution of the time-dependent Schrödinger equation. And you have to look pretty hard to notice any differences here. This is even though the TDSE includes rescattering here, but it doesn't play much of a role. Now, for a negative ion, the SFA is also good if rescattering is included. This here is an experiment by Igor Kiyan 10 years ago. And the upper part is the experiment. You see the rescattering plateau here. And the lower part is the theory, now including the first term. And again, on this scale, the agreement doesn't leave anything to be desired. Now, this is negative ions, but of course, we are interested in atoms. Now, even for an atom, the direct SFA is not hopeless. If you focus on the region here transverse to the propagation direction of the field, then you see here this pattern, which at the time we called the carpet. And the carpet again is very well described by the SFA. Here's the experiment again. Here's a TDE simulation. And here's the SFA. And only including the direct electrons, no Coulomb field after the electron got out. How come? That the situation is this, that at right angle to the field, if you were to Coulomb correct the electron states, then both direct orbits would be affected equally. So if you calculate the phase difference for interference, the Coulomb field would actually drop out in that case. Now in the field direction, it's a totally different story, because now the two orbits, the two direct orbits, are affected very differently by the Coulomb field. The short orbit is not at all, and the long orbit very significantly. I'll come to that later. Okay, the SFA, as I showed it, is already perfect. I mean, you have compact expressions, only integrals that you have to evaluate. But the integrals are strongly oscillating, and it simplifies the problem enormously, and also gives you a lot of physical insight if you evaluate the integral by saddle point evaluation. And in order to do that, you look at the oscillatory parts, the phase here that oscillates, the action actually, and you look for those values of the integration variable, which is the time of liberation, the ionization time, and the rescattering time, and also possibly the momentum in between. So you look for those values that render the action stationary. So that gives a couple of equations, and here it is again. So the first one describes energy conservation at the time of ionization. The negative sign here indicates that you are not going to get real solutions for these times. The second equation here describes the condition that the electron return to the ion at the time t, and this one here accomplishes elastic scattering at the time of return. So the solution of these equations, here they are in pictures again, the solutions of these equations define quantum orbits. Each solution then has to be inserted here into this phase. There's a prefactor which doesn't matter very much, and then you have to carry out the sum. The sum extends over all quantum orbits, and there's quite a number of them, infinitely many, depending on the situation. All of these have to be summed up. And each solution defines a quantum orbit, which just gives you the trajectory of the liberated electron in space and time, before and after rescattering. So that's a picture. Okay, these are complex still, but the real parts can be drawn. And that gives you a picture of what happens when you consider ionization into a state with final momentum P. So a summary is that it's an enormous simplification of the original problem. You only have to find the solutions of the saddle point equations. So rather than having to do the integrals, you just have to solve the system of two algebraic equations. And this works for any number of dimensions, any external field, any polarization, etc. And you get for free a very appealing, intuitive picture of the underlying dynamics. Now, of course, there is a word of caution. It's fairly easy to solve the saddle point equations for linear polarization. But in other cases, it can be very cumbersome and it's easy to overlook some, etc. Okay. So for linear polarization, the simple man model gives you a very easy overview. And normally this picture is shown in this context here, where you have here the start times, and then you have the various electron trajectories departing of the ion, returning, never returning, etc. But I prefer this picture here, which has a lot more information in it and is much simpler. What's plotted here, the curve, is the integral of the vector potential. If you have a monochromatic long pulse, then this is proportional to the electric field. You specify the start time here, right here, and then you put the tangent to this curve at the position of the ionization time, and you look for the intersections of this straight line with the curve, and that gives you the recollision times. So in this case, there are three solutions, and now here comes a very important point. I showed you that the first order rescattering term only accounts for electron-ion interaction once. So this here actually corresponds to three terms in to the ionization amplitude corresponding to this, or this return time. And if you would like to have the term that accounts for the fact that, for example, an electron that returns here has already seen the ion twice before, then you would have to go to the third order term in the expansion, which nobody has ever done. So that's a limitation which is often overlooked. One has to discriminate between rescattering and revisiting. An example of the fact that you need to consider sometimes very many solutions is very old here. Data are from the last millennium. What's plotted here is a part of the ATI spectrum for different intensities. Intensity goes up here from the lowest to the highest trace by only 5%, and you see that this group of peaks here rears up by almost an order of magnitude. And here's an SFA description, which is, works pretty well, I think. And also, you can now make a statement about the underlying physical reason. You get this picture here by summing over a large number of these longer orbits. And the enhancements, the parameters have to be such that you are at a channel closing, and then and only then you get a constructive interference of all these higher order contributions. This is for linear polarization. Here's a corresponding picture for a bicircular laser field. Again, if you consider constant electron energy, for example, then you see here these enhancements coming up at intensity differences that correspond to channel closings. Another example of what the SFA can do is the low energy structures. We look again at this picture here, and okay, you start here at the ionization time with a tangent. This corresponds to the fact that the electron starts with zero velocity. Now it's possible, like in this case, that the electron also returns with zero velocity. So that would be a soft recollision. And now if you modify the start time only very slightly, then the picture is this. So the soft recollision has dropped out of the picture. So this situation here corresponds to a cutoff of the spectrum. You have a solution contributing up to some point, and then it drops out. So in classically, this is sharp. Quantum mechanically, it's smoothed out a bit. And these cutoffs are visible in the spectrum and define the low energy structure. You also see here that such a soft recollision is invariably preceded by a hard recollision, which, however, is not part of the picture once if you are restricted to the first order term. Okay, you can keep going here to the, here this again would be another soft recollision about one period after the first, and that way you get a whole series of LES, which corresponds to the decays that has been seen in experiments and also been obtained by other approaches. Let me return for just a minute to the direct orbits. So these are the orbits here that correspond to direct ionization. It's 2 per cycle, and they lead into the same final momentum state because the final momentum is given here by the slope of these straight lines. And now here you see the short orbit and the long orbit. The long orbit revisits the ion, but this is not part of the description by the 0th order term. And if you want this to be part of your description, you have to move to the first order term. Now in the first order SFA, the same orbit also contributes here to rescattering. This can be forward rescattering and then a superposition of the direct orbits from the 0th order term, and this here from the first order term will generate the famous holographic structures. So I would like to emphasize that different people understand different things by the direct orbits. For SFA people, these are the 2 orbits that contribute to the 0th order term. If you are a trajectory guy, I mean a CTMC person, then this orbit here would interact with the potential all the time. So depending on the situation once, or if it goes this way several times, and all would be the same time, and people call this the direct orbit. So one needs to be aware of this difference in language. Okay, back to the cutoffs. Now here's a pretty complicated picture, but it's still the simple man picture. And now here the lines denote all the cutoffs, so that solves the saddle point equations, also as a function of angle. So let's return to the, I have some notation here for these orbits, which however I don't have the time to explain, never mind. Let's look at the simplest situation here, that's up here. So here are the high energy cutoffs of the plateau. You see here the light blue line is a 10 UP cutoff, and then you have a series of other cutoffs at lower energies that correspond to longer and longer orbits. They converge ultimately to a limit here of 8 UP, which is a dashed line. Then here, if you change the angle, you see what happens to these cutoffs. And the situation here near the origin is especially rich and colorful and interesting. And let me show you a blow up of this, which is right here. And now here you see a lot of, first, I mean, you recognize the LES series. In the field direction, it's here. And if you move off axis, then these energies move. So then here, there's a lot going on. We call this the fork at the time, because here is sort of one bunch of cutoffs here and another one here. And in the middle, this forms the middle prong of the fork and it splits up again. And all of this is due to longer orbits. And then you have one by here, you have a V structure that I'm going to show you, etc. So all of this is a simple man model. Here, for example, is an SFA calculation of this V structure, which you can nicely compare with the data in this paper by Volta et al. And here's a fork. You see it here. And in this picture here, we have tampered with the color coding a bit. So now here it jumps out more clearly. You also see here the spider. And here you were to see the LES if the resolution were better. Now, this here is for a fairly long pulse. It's interesting what happens if you shorten the pulse. Here it's down to 2 cycles, and you see the fork is gone. And the reason is, again, becomes very clear in terms of quantum orbits. The fork is generated by longer orbits. And for a short pulse, the longer orbits just do not have time to unfold. The spider, on the other hand, survives. So that's generated by short orbits. Here's the famous holographic structure paper. And actually, it also shows all these features here. Even, I think, they were not addressed in that paper. Here is the SFA calculation, including the zeros and the first order term of the Born series for a long pulse and for a short pulse. And you see all these structures here that I was just pointing out. Now, you may have noticed that I did not mention the potential with just one word, even though many people will tell you that the low energy structures are due to the Coulomb field. Now, this is partly wrong, in my opinion, and partly not. And the reason is this here. Normally, of course, the rescattering term is completely dwarfed by the first or by the 0th order term in regions where both contribute. And but this is not necessarily so if you have a Coulomb potential, because the first order term incorporates the scattering amplitude, and that goes like 1 over the momentum change squared, and it's actually divergent for forward scattering. So this acts here like an amplifier of the rescattering term and has a consequence that these low energy structures are indeed visible on top of the direct electrons described by the first term. Okay, another example, let me consider ATI in a bicircular field. Here finding the solutions is much more complicated. Okay, here is the electric field, the black line. We consider equal intensities here, and the vector potential. And the 0th order term, which the spectrum of which is given here, you expect the spectrums to be opposite to the vector potential. So the electron comes out preferentially exactly at right angle to the maxima of the field, as you expect. Now, this is a first order term, is a 0th order term. And you also see it has 2 kinds of symmetries, rotational symmetry by 120 degrees and reflection symmetries about 3 different axes. Now I turn on the interaction term, looks like this. And you see immediately that the reflection symmetry is gone. And you also see here that the electron, if you superpose the 2 terms, the electron would no longer come out in the direction of the vector potential, but there would be some offset angle here, which depends a lot on energy. Okay, another feature here are quantum orbits that are contributing to ATI in a bicircular field. And okay, let's see what these orbits do. This here is the result of 0th order plus 1st order calculation. Ideally, this would correspond to an experiment. So let's assume that an experiment would also look like this. And now you want to know what is the origin of certain electrons here in this velocity map? How do they get out? What do they do once they are in the continuum? So in order to answer that question, you can separately plot the contributions of individual quantum orbits. So here are 3 examples. 2, this is forward scattering, this is forward scattering, at comparatively low energy, and this here is a backscattering orbit. Now you can superpose these, so that gives a picture like this. And now you can indeed draw the conclusion that this feature here in the measured, ideally, spectrum is actually generated by these quantum orbits. And these quantum orbits here look like this. This here is this picture. All the orbits are drawn for an ultimate angle of 50 degrees outside the field for the electron to make with the polarization axis. So you can actually, for any part of this velocity map here, you can identify the corresponding dynamics of the electron in the continuum. Okay, change of gears in my last minutes. Let's just consider pure Coulomb scattering, no external field. So if you want to calculate the cross-section, then you have to sum these Feynman diagrams here. The first one is quickly calculated and gives a standard result, the Rutherford cross-section. But now you want to do a better job and also include some of the subsequent diagrams. And then you will notice that these contributions here actually diverge term by term. And if you somehow tamper with this divergence, then you will get a result that is wrong. It differs from the Rutherford cross-section. So the upshot is that in this case, this holds for a Coulomb potential and only for a Coulomb potential. The first order already gives you the exact cross-section. And turns out that if you want to do it, you can actually, with some screening or something, to handle the divergence, you can calculate all the higher order terms, sum them, and then you will notice that the sum, all the divergences are absorbed into a divergent phase, and the prefactor of the phase just corresponds to the Rutherford cross-section. So this is a unique situation for a pure Coulomb potential, related obviously to the fact that the Coulomb potential has no parameter in it, no parameter of a length or anything. Okay, now if, of course, we want to do this on the background of a laser field. Doing this is very easy. You just have to replace a straight line by a double line, which indicates the Volkoff propagator. And then you have to try to do the same thing with the Volkoff propagators, and that's of course no longer easy. And okay, the hope or the question is, would the same mechanism still apply? And the answer is, of course, no, it won't. But on the other hand, I believe that this Coulomb mechanism is still lurking somewhere just below the surface. And it should make itself somehow noticeable when you do all these higher order calculations. Here is a recent calculation by Jing Chen and collaborators, and he actually managed to calculate the first 5 terms of the Born series corresponding to 0, 1, 2, 3, 4 real rescattering events, not just revisits, rescattering events. And here you see the results. This here would be the direct electrons, and then as of one interaction, you have the plateau. But now, if you include more and more terms, it grows. And this, of course, the suspicion is near at hand that if you keep going, the series will diverge. I mean, in order to avoid it here, he screened the Coulomb potential a little bit. Okay, so the suspicion is that for a Coulomb potential, actually the Born series will diverge. So what should be done about it? Well, we don't really know. The idea would be ideally to manage to sum all the forward scatterings of the electrons in order to get something like a renormalized electron propagator. And so then forward scattering would be removed from the interaction, and then hopefully the Born series would quickly converge in terms of this renormalized interaction. But well, this is science fiction, and we have not been able to do this. Okay, So I promised kind of a list of what effects are covered by the Bond series and what are not. And here's a list for effects that are incorporated, that can be handled with the Bond series is quite long. And the opposite list is much shorter. It definitely, I think, includes this 1 to 2 UP plateau, which was recently discovered by the chairman and by Sergei Potrushenko and Thomas Keil. And I think also the very low energy structure should be on this list, but I'm not quite sure about it. And also the zero energy structure. Okay, let me just finish by showing a list of references. Here, of course, top of the list is this beautiful review by Carla and Andrew Maxwell. And that has everything in it that they tried and other people have tried to improve on what I was talking about. And there are other review papers here, and there are other papers that I consider important. And so thank you for your attention, wherever that might have taken place in space.
Thanks very much, Wilhelm, for this nice overview. So we have time for a few questions. I see one question by an anonymous attendee. It's difficult to unmute an anonymous attendee, so I just read it. Could you please comment how comes that the two-cycle pulse photoelectron distribution is so symmetric? Is this just two cycles out of infinitely long constant envelope taken into account?
The reason in that case was that they averaged over the carrier envelope phase. So that otherwise, I mean, if they had had a specified CEP phase, then depending on the value of that phase, they would have observed forward-backward asymmetry. But I think in the data it was averaged.
Okay, the next question is by W. Kwan, so probably we can unmute you so you can ask yourself. Please speak. Okay, then I just read it. Would you mind discussing more on the uniform approximation? What kind of problem can be solved by it?
Okay, hi, Wei, that's what you are, right? Anyway, so the uniform approximation, I didn't have time to explain it. I cited a reference. The uniform approximation is important when two saddle points approach one another very closely. This is always the case near a cutoff. Okay, and then the standard saddle point approximation doesn't work anymore. Actually, what you have to do is at some point, which you have to pick deliberately, drop one of the saddle point solutions. Otherwise it blows up. And if you use a uniform approximation, then this does a job for you. And it treats the two saddle points as one unit and automatically disposes of one after the cutoff. Carla, by the way, is the expert on this. She has used it in very many papers, and it works beautifully.
Okay, the next question is by Jens Biegert. Jens, please.
Good morning, everybody. Very nice talk, Wilhelm. I was just wondering, the bicircular field that you showed and this angular offset of basically the emerging electron wave packet, how it goes out. Do you think this could be a useful probe of more of the structure of a Coulomb field, for example, of a molecule, even if volume averaging would come into place?
Well, volume, excuse me, volume averaging, of course, is a problem. I mean, I think actually, but I don't know, because we hadn't really made this connection until quite recently. I think that if you use the Coulomb potential for this calculation, then it would give you the right offset. I mean, the one that you also receive by solving the TDSE or so, I mean, to the extent that the SFA is applicable. But we haven't done this. And okay, for a molecule, the SFA can be done, has been done in many papers, but it's a bit problematic because for a molecule, the inherent gauge dependence of the SFA makes itself visible in some obnoxious way. But actually, you remind me of a point, I mean, which I forgot to mention, that in my opinion now, the treating the Coulomb potential just to first order in the first order rescattering term is much better than people, including myself, used to assume until recently. And the possible origin is what I was talking about in the end.
Okay, I don't see further questions, so let's thank Wilhelm again. I clap my hands here. And move on to the next talk by Hardy Gross, who is now at the Fritz Haber Center for Molecular Dynamics in Jerusalem. And he will talk about ultra-fast laser-driven spin dynamics, predictions from time-dependent density function theory. So please.
So welcome everybody. Let me first share the screen. Does not. Does not seem to work.
How can I help? Are you using the green button through?
Yes, that's what I'm doing. Well, before the session it worked.
It's always the way.
Interesting.
Is it possible to close your PowerPoint presentation and reopen it?
Let me try that. Sorry about this delay.
Great, it's working.
Okay. Now it seems to work. Can you see the screen?
Yes, that's working now.
Okay. So welcome everybody. I first want to thank Carla, Andrew, and Bridget for putting together this wonderful program, but also for the very clear and elaborate instructions on how to deal with this novel format and the discussion rooms and all this. So it really worked perfectly until I started trying to share my screen. So this is a methodology session, and I will talk about time-dependent density functional theory. In particular, the calculation of the real-time spin dynamics. The motivation for this it's not forwarding. Something is wrong. Here we go. So the motivation is to make memory devices and storage devices faster. Typical magnetic random access memory, as well as the magnetic hard drives, work on a time scale of around 1 nanosecond per bit. As you know, in recent years, these magnetic devices have largely been replaced by so-called solid-state drives, SSDs, that do not work with magnetism, but they are of a similar speed. So it's again around nanoseconds per bit. And the crucial question is, can we make this somehow faster? I will try to answer this question, and indeed we can even go down to attosecond processes with the switching of magnetization, as I will demonstrate. My talk has 3 distinct topics. First is laser-induced demagnetization. This is more like an old topic. This was found experimentally in 1996, and I would claim it is now fully understood with TD-DFT calculations. An important aspect there, as I will show, is time-dependent spin-orbit coupling. Then a very different topic is a process that we termed OYSTER, the optically induced spin transfer. It works on a much faster timescale, so laser-induced demagnetization works on a timescale of 50 femtoseconds. This process, OYSTER, works an order of magnitude faster. It seems to me popular in this field of physics to name effects after animals like rabbit or spider. So we have added an oyster to this here. It was an effect that was predicted with TD-DFT in 2016 and found experimentally 2 years later. First by the Eschliman group in Kaiserslautern, and then by several other groups as well. So that's the second topic. And the third topic will be, since this is a methodology section, an important aspect of what a good exchange correlation functional is for this kind of non-collinear magnetic effects. So this first topic, laser-induced demagnetization, started with this experiment here. It's in 1996 by the group of Bigot and Beaurepaire. And what you see here is that as a function of time, the magnetization, this experiment was for nickel, bulk nickel, goes down significantly. That's what you see here on the time scale of about 1 picosecond. Now, by now, one knows that one can do this even much faster of a time scale of, let's say, something like 50 femtoseconds. But if you think about it, this is quite surprising because with the intensities that were used, the laser does not act directly on the spin, right? So the magnetic component of the laser is very small. So there's no direct interaction with the spin. So how can this be that this happens so fast? And there have been many propositions in the laser. First was a study that actually investigated the importance of the magnetic component. Then another proposition was spin flip electron phonon scattering. And finally, spin transport, where the idea is that in the interesting region where the laser focus is, there's initially some magnetization which then moves elsewhere in the material so that the magnetization inside the laser spot goes down. So all these 3 effects exist, there's no question, but it turns out if you look at it within ab initio calculations, the first one and the second one are too slow. They don't account for this very fast demagnetization. This effect is there, and it's an important aspect. But what we found, it's only half of the story. There's another half which has to do with spin orbit driven spin flips that I will discuss in the following. Okay, now when we talk about magnetism, the quantity of prime interest, the object that you want to calculate ultimately, is the observable that is called the spin magnetization density. It's a vector field. So think about it. If you have an electron that moves throughout otherwise empty space, then one can say, well, this electron has a spin and it has a charge. But then in a solid or in an atom or a molecule, then we have a wave function. So it's not really a good idea to talk about the spin, right? What, like for the charge, like there's a distribution of the charge, and likewise there is a distribution of spins, and that's exactly this object here, spin magnetization. So here's an example that's a chromium monolayer. I will come back to this later, and the way I present this throughout the talk is with a color coding for the absolute value of this vector field. So this guy is plotted here, the absolute value, and these little arrows, the little white arrows, they all have the same length, and they just indicate the direction of this vector field. So this is the quantity we want to calculate, and the theoretical approach is real-time TDDFT. Here's the equation. So it's a weakly relativistic generalization, one could say, of the original Runge-Gross equations. So let me discuss the terms here. This is the time-dependent Cohen-Sham potential. It's a scalar potential. And this object also appears in this time-dependent spin-orbit coupling term. So it's really something else than the usual spin-orbit coupling. Usual spin-orbit coupling is time-independent. It's just the nuclear potential. This is the time-dependent Cohen-Sham potential that appears here in the standard spin-orbit coupling expression. Then furthermore, there is a Zeeman term here involving a Cohen-Sham magnetic field. And these two quantities, the Cohen-Sham potential and the Cohen-Sham magnetic field, are given by the standard expression, external potential given by the lattice, Hartree term, and an exchange correlation potential. And in the absence of external magnetic fields, the Cohen-Sham magnetic field is just given by the exchange correlation part. And it's these two objects, the exchange correlation potential and the exchange correlation magnetic field, that are universal functionals of the density and the magnetization density. So as you can see here, the vector of Pauli matrices appears here. So the eigenfunctions, or in the static case, eigenfunctions in the time propagation, time-dependent orbitals are Pauli spinors, so two-component objects. And finally, the laser field is given by this time-dependent vector potential. So once you have these Pauli spinors, the density and the magnetization density are calculated from these standard formulas. Now, since this is a methodology section, I will talk about a couple of aspects of the implementation. What we want to describe is cases where the wavelength of the laser is in the visible regime, which means that the wavelength is very large compared to the unit cell. So it should be a good approximation to do the dipole approximation, which means that the electric field of the laser is assumed to be spatially constant, which means that the vector potential that I showed you in the equation is purely time dependent. So this is numerically extremely important because if it's purely time dependent, the spatial periodicity of the Cohen-Sham Hamiltonian for a periodic solid is preserved, which means that we can implement these equations more or less straightforwardly in a band structure code. And this is done here in the ELK code. It's an LAPW code. And so the people who are the main developers of this code are Kay Dewhurst and Sangeeta Sharma. The acronym ELK stands for electrons in K-space, or some people say, since the main developer is Kay Dewhurst, that it's actually electrons in K's space. And so these two people managed to make this band structure code time dependent. So here's now first result, calculation for iron, cobalt, and nickel bulk. In the first line, you see the laser field. So it's a pulse of about 6 femtoseconds or so. And this is then the magnetic moment. So it's the magnetization density integrated over the unit cell as a function of time for iron, cobalt, and nickel. And you see, indeed, it goes down. So it's normalized here to the initial magnetization. And what is interesting is that during the laser field is on, not so much happens a little bit here, but the main effect actually happens after the laser field is switched off. Now, let's analyze these results a little bit. And one nice thing in these ab initio calculations is, as opposed to experiment, is that we can actually switch off certain terms. And in this calculation here, we have switched off spin-orbit coupling. So if you look at the spin density, there's wild commotion, right? But as you integrate it to calculate the total moment, it stays put. It stays at this initial value, no time dependence. You see that you see nothing. So can we understand this? And there is in fact an exact equation of motion for the spin magnetization. I've written it down here for the Z component. And it has 3 terms on the right-hand side. So this is divergence of the spin current tensor given by this expression. So if we had only this term, then it would mean that the Z component of the global magnetization would be conserved. This would be a continuity equation. But there's other terms, so it's not conserved. And the first term is what is called the local spin torque. You see immediately it's the Z component of a cross product, M cross BXC. And the second term you can see immediately from the 1 over C squared here comes from spin-orbit coupling. Now, if we integrate this equation, both sides, on the left-hand side, then we get the time derivative of the global moment. And on the right-hand side, we get the integral of the spin torque. We get then the global torque exerted by the exchange correlation magnetic field. And there's a rigorous theorem, it's the zero torque theorem, saying that this integral has to be 0. One can prove it mathematically, but it's physically totally plausible. Exchange and correlation comes from the internal forces from the Coulomb interaction. So the internal forces cannot exert a global torque on the whole system. So this has to be 0. It's perfectly plausible. This term is 0, it's continuity. So the only term that can actually change the global magnetization is spin-orbit coupling. So in this last calculation, we have put spin-orbit coupling equal to 0, and hence there is no change, right? That was the calculation. So it's perfectly clear. Now let's investigate this a little bit further. So what I showed was the global moment of the Z component, because initially these 3 materials, iron, cobalt, nickel, are collinear. So what could be, in principle, especially if you think of things like magnons, is that the initial Z component would have kind of been transferred to an X and Y component so that the Z component changes, but this is not the case. So as you can see here, the X and Y components stay throughout the propagation very small. And now this is the main interpretive transparency here. We have now decomposed the total magnetization that goes down here, that's the same as what we saw before, into a part that I call excited. So that's electrons that have been excited by the laser pulse. So they are not near the atom anymore, near the atomic centers, but they have been moved elsewhere in higher bands in the interstitials. And their magnetization goes up, while the magnetization of the electrons that have stayed near the atomic centers goes down. And the sum of the two is the total curve that we saw before. Now, the fact, so this is what happens. One could say, well, it's kind of an optical excitation. The electrons that are excited elsewhere in space take spin with themselves. So near the atoms, the magnetization is reduced. Now, the interesting thing is that after the pulse is switched off, this part stays largely constant, changes slightly still, but the global magnetization basically follows the reduction of the magnetization of the remaining electrons, right, near the nucleus. So this is a universal feature that we found in all calculations. And it's also very plausible because I emphasized before that the main cause of change of the magnetization is spin-orbit coupling. And spin-orbit coupling is, of course, much larger near the nucleus because the potential is larger. So this is the effect of spin-orbit coupling. So this is summarized, this finding here. So initially, the laser moves magnetization from the atomic centers elsewhere, and then spin-orbit coupling drives the demagnetization of the more localized electrons. So we can play a little bit with the intensity and the pulse duration here. So you see that a similar decrease in magnetization that you see in blue here, that can be achieved with a high intensity short pulse, can be achieved the same reduction ultimately also with a longer pulse that is weaker. So what counts in the end, what this shows is that the relevant quantity is the fluence. Now what I showed so far is 3D bulk. Now let's look at other systems, and here's again our chromium monolayer. Right, so here are the chromium atoms, right? And the color, remember, is the absolute value of the magnetization. And now let's propagate with a laser. So here's the electric field. And here's a time counter. And what you see here is the main thing, apart from this wild commotion that you see, is that you have a strong reduction of the magnetization near the nucleus, right? The initial picture was this, right? Strong magnetization here near the nuclei, and at the end, it was reduced strongly to a much lower value. So this tells you that this demagnetization is a local process, right? It happens near the nuclei. And this also means that it really doesn't matter what system you're looking at. If this is a chromium cluster, right, you will find exactly the same thing. And indeed, there were calculations by the group of Stefano Sanvito in Dublin who found exactly the same effect for magnetic clusters. So now another calculation for a nickel slab. There you see that this demagnetization is more strong in the slab than in the bulk. And this was with a realistic experimental laser pulse, and this effect was also found experimentally. This is now a comparison with the other mechanism that was proposed in the literature before, namely if you have such a slab here of nickel, which initially is magnetic, and aluminum, which initially is non-magnetic, then upon the laser pulse, you see two effects. On one hand, the reduction of magnetization due to spin-orbit coupling that I just showed you, but there's also magnetization flowing away from the nickel part into the aluminum. So it goes away from one part of the system to another. And so this is, as you see, the magnetization nickel goes down as a function of time, and in aluminum it goes up, right? This is what you see here. It's a relatively long pulse of 50 femtoseconds. And if you then compare calculation with and without spin-orbit coupling, you see that without spin-orbit coupling, so only this transport mechanism, leads to a change of magnetization of 25%, while with spin-orbit coupling, you get 40%. So these two effects are about of equal importance. Okay, so here's a paper that I want to mention that was a collaboration with the Bigot group, where this relative importance of spin transport and spin-orbit coupling induced spin flips was also confirmed experimentally. And the whole thing is also in a very recent review article, just appeared a couple of months ago here, together with the San Vito group, where these calculations for magnetic clusters are also contained. Now, second topic, very different. It's the oyster effect. So we did a calculation on a different material, otherwise pretty much the same kind of TD-DFT time propagation. This was for a material that is so-called Heusler compound, nickel, manganese, antimony. And here, so this was very short laser pulse of 2.5 femtoseconds. Here are the laser parameters. And what we see is a very fast decrease of the magnetization on the nickel atoms, and at the same time, an increase of the manganese atoms, sorry. So manganese goes down, and at the same time, an increase on nickel. What you also see, there's a slight increase of magnetization on antimony, and the magenta curve here is the delocalized electrons that cannot easily be assigned to one of the three atoms. This is interstitial regions where the electrons can also go. So this is what we found. And this is incredibly fast, right? It's 3 femtoseconds where this process happens. And imagine you could make magnetic devices with switching times of 3 femtoseconds. This would be a gain of 6 orders of magnitude in speed. So this would be fantastic. I mean, we don't have a device yet. This is not my job. But this was the prediction of TD-DFT. So can we understand this? And the first line here of this transparency is still calculation, and the two other lines are interpretation. So what you see here in the first line is, as a function of time, integrated spin density, so the number of spins, if you wish, on manganese and nickel, and delocalized as it changes in time. So you basically, that's the meaning of this plot, is you increase the number of spin down electrons by 1 on manganese, and you decrease it by a little bit less than 1 on nickel. For upspins, you have a large contribution of delocalized electrons. Nickel happens nothing, but you decrease the number of electrons on manganese by 1. Okay, so in the very simplified picture that is depicted down here, you see exactly that. So this is the initial configuration of nickel. So there's very little magnetization, it's been saturated. And then with the laser, you induce a transition from nickel to manganese of a downspin. And you also induce on manganese, where the main magnetization initially is, of an upspin to the interstitial region. So if you then look at the magnetization of manganese before and after the laser pulse, you see initially this is 4 spins up, 1 down. So this is effectively magnetization of 3 spins up, while after the laser you have 3 up and 2 down. So effectively it's 1 spin up. And this is exactly what you saw in this plot here, the strong decrease of the manganese magnetization, right? So when does this happen, or why does this happen? And here is very useful to look at the density of states that is present in the initial ground state. And this is plotted here. So this is upspins. That's the occupied upspins and downspins, and that's the unoccupied upspins and downspins. And what you see immediately here is that there's no empty states available. So the upspins can at best go to the interstitials to somewhere else. And that's exactly what happens here, right? That's what we saw here. While the downspins, there is empty states, but the empty states are on the other type of atoms. So you have a downspin occupied here. Blue is nickel, on nickel, but available empty states are only on manganese. And it's important to realize at this kind of intensity that we have, the laser does not flip the spin, right? The magnetic component is small. So you have to go from a downspin orbital to another downspin orbital. And the only available downspin orbitals are on manganese. So what you do in an optical excitation, you actually move the electron, including its spin, its downspin, from the nickel sublattice to the manganese sublattice. So from one region in space to another region in space. So you change the local magnetization. You don't change the global magnetization, but locally you change it. That's the oyster effect. It's also clear that this cannot always happen. So this is what I depicted here. This is what we saw before, nickel, manganese, antimony. But then it depends on what kind of states are available. So this is for another material, cobalt-2 manganese silicon. And here you see the available states at a certain frequency are actually on the same atom. So in this frequency regime, you go from, in this case, cobalt to cobalt, and this effect, oyster, does not happen. It's immediately clear, right? And then there's more complicated cases where both the downspin electrons can move from one atom to another and the upspin electrons can move. This is for a compound manganese-3 gallium. This is especially tricky. This is a ferri magnet.
Hardy, sorry to interrupt.
Almost done, almost done. 1 minute. Where you have a ferromagnetic, so this opposite spin arrangement of the spins, but they don't compensate, so it's not an anti-ferromagnet. but it's a ferromagnet. And then if you put all these pictures together that I showed you here on the lower plot where the spins go, you see that you have here for this material a ferri to ferro transition within a few femtoseconds. Now, as I said before, this oyster effect was first predicted by TDDFT in 2016. In fact, these examples that I showed you were from the paper of 2016. And then later it was found, confirmed experimentally by several groups. This is one of the papers of the Ashleyman group. And I just want to highlight here, so they do it even faster, right? So in sub femtosecond regime, and they call it the birth of the research area of attomagnetism. Right? But it's exactly the same mechanism as you see here, right? The transfer of spins from one to another sublattice. This is for nickel iron alloy. Okay, so I will not talk about the functionals. This is a different topic. I just want to summarize here. So I showed you two effects: demagnetization within something like 50 femtoseconds, which is a spin orbit driven and spin current effect. You don't change the components much of the non-collinear magnetization. What we found is that interfaces and layers have equally importance in the spin current and spin orbit coupling effect. And finally, I demonstrated this new effect that we called oyster. And I did not talk about the last topic, the non-collinear exchange correlation functionality. Thank you for your attention.
Yeah, thank you, Hardy. We have one question by Daria Gorelova. Please ask your question.
Hello, can you hear me?
Yes.
Yes, I can
Yeah,
hear
great.
you.
So yes, so thank you. So unfortunately, I cannot turn on my video. So thank you for your great talk. It was really great, and it brought me to the time of my PhD when in 2013 finished that I was also doing on theoretical ultrafast magnetization dynamics. So could you please come back to your slide for the first part of your talk where you have shown the equation for the time-dependent equation for equation of motion for magnetic component, and then you have the effect of the spin-orbit coupling.
Yes.
So maybe could you speak a bit more about kind of intuitive explanation for that? So of course we can see the equations and understand that if you switch off this term, so there's no spin flip, but could you speak a bit more? How do you see it? How do you understand that?
Okay, so I talk about this, the integrated version. The other equation was just without the integral over the unit cell. So there's three terms here. If the Z component of the magnetization, this is what we are looking at here, the time evolution of the Z component of the global magnetization. If this was conserved, which it is not, but if it was conserved, then we would have only this term and this term, which is a continuity equation.
Mm-hmm. Yeah,
that
I understand.
That in fact change the magnetization, or that can change the magnetization. Now, here's this term, which is the curl of M cross BXC, which is the cross product, sorry, of M with BXC, M cross BXC. And if you had, in addition, an external magnetic field, right? So B external cross magnetization, this would exert a global torque on the magnetization of the system. So you would change, you would cant the global magnetization. But the internal forces cannot do this. So that's why this term is zero. Now, this is spin-orbit coupling. It changes the direction in a complicated way. One thing that you can actually also prove, which is complicated, but you can prove it from the equation, is that initially, at the initial point in time, after you, at the time you switch on the laser, so at the initial ground state, the first moments, this leads always to a decrease of the magnetization. What happens later, we don't know, all kinds of things can happen, but initially you always decrease. That follows from this term here. That's another interesting aspect.
Yeah,
Okay,
thanks.
we have to move on. There are two other questions and they will be moved to the Slack workspace. So thank you, Hardy, again.
Thank you for your attention.
Thank you. The next speaker is Manfred Lein from Hanover, and he will talk about two-color methods in strong field physics.
Thank you, Dieter. Okay, I had some technical problems in the morning, so let me see if it works now for me. Can you see my screen now?
Yes, I can see it.
Okay, it tells me that my video was stopped by the moderator. I'm not sure what that means.
Can you move your pointer? So, yeah,
You cannot see the pointer?
I can see it, yes.
Okay, but you cannot see my face, I suppose?
No, not at the moment.
Yeah, okay. I think it has been switched off by the moderator somehow. At least I don't know why. Okay, now it should work again. Okay. Now, do you see the talk and myself?
Yes. Yes, I can see you.
Okay, thank you very much. Okay, so it's a great pleasure to be here. Thank you, Carla, Andrew, and the other guys for making the big effort to make this event possible. I suppose it's one of the few proper conferences that we get to attend this year. So I want to speak about two-color methods in strong field physics. This is mainly about work that has been done by the two PhD students, Sheng-Chun Yue and Nicolas Eike in my group. You can see them on this picture. Jun is the guy in the back left with the victory sign, and Nicolas is here. If I have enough time, I might also say a little bit about non-dipole effects calculated by Simon here. Okay, but before I go into that, I will first show you, because these are the quantum battles, I first show you the weapon that I brought. This snake here is a very interesting one. Some people call it a flying snake. And it can actually fly using two-color waveforms, using very much the stuff that I discuss here. Actually, one minor detail here is the snake has some interesting fast cars put up in his cage. Maybe the chairman can recognize what that is. But let's come back to the snake. If you don't believe that this snake can fly, or let's say glide through air at least, please go to this YouTube link to view the flying snake in action. And there has actually been a Nature Physics paper published very recently, just last week, where some biomedical engineers have done measurements on this flying snake. And so what they find is that this snake does some kind of undulation motion while it glides through air. So here in panel B, you see a top view of the snake. And what they have found out is that there are two kinds of waves. One wave is such that the snake makes displacements in the horizontal direction at a certain frequency. That's the blue curve. And the other wave is displacements in the vertical direction at 2 omega, twice the frequency. And they even find out there is a well-defined phase relation between the two waves of 90-degree relative phase. And they argue that the purpose of this kind of two-color waveform is to keep the snake stable as it glides through air. Okay, so that I think is a very nice example of a two-color waveform. Of course, our setting is a bit different. We look at atoms and molecules in the gas phase ionized by strong femtosecond laser pulses. And the central question that I want to ask throughout the talk is, how can we define and observe the time of ionization? So to make it clear at once, I am not talking at all about times needed for a particle to go through a tunneling barrier. When I speak of the time of ionization, what I really mean is the time of departure of the electron. And I will show you two methods how we can see these times. One is based on high harmonic generation, and the other one is based on an Attoklock type scheme. This is a brief list of previous work using two omega fields for measurement of ionization time. Probably the list is not complete. I think there has been some work also done by the Imperial College group. Also, Katerina Wotzi yesterday showed us interesting new results from her on this topic. So basically, it's important to realize that there are these two possibilities. We can have the two polarization directions of the omega and 2 omega field either orthogonal to each other or parallel to each other. And I will address both cases in this talk. So let me first remind all of you about the three-step model of high harmonic generation. I think almost everybody is familiar with it. In the three-step model, we think of the atom first being ionized by the presence of the strong field. In the second step, we have an unbound electron that is accelerated away and back to the parent ion. In the third step, the electron recombines with the parent ion and emits a photon. And this gives rise to the typical shape of the observed emission spectrum from such a system that shows a cutoff at a certain harmonic order that is simply related to the maximum kinetic return energy of the electron. The quantum mechanical version of this is also well known to many of you. We call it the strong field approximation or the quantum orbit model. Wilhelm has explained a lot about quantum orbits already in his talk. So the point here is, in contrast to the classical model, times become complex. So in these equations, the Ti and the Tr are the complex time of ionization where the electron starts and the time of recombination when the electron goes back into the initial bound state. And these are the three saddle point equations that you need to solve to find these two complex times. Okay, now the question is, can we actually set up a scheme to measure these times? And the answer is yes. Already many years ago, Dudovic and co-workers introduced this two-color scheme where we have high harmonic generation by a fundamental field with a strong fundamental with frequency omega and a weak 2 omega field polarized in the perpendicular direction. So this additional field somehow probes the electron motion. It moves the electron trajectory sideways in such a way that the electron might miss the parent ion when it comes back. So only for a certain suitable two-color delay, that's the relative phase between the two colors, will you have the situation that the electron can come back nicely and then you have a high harmonic yield. That's what they have called the displacement gate. There's also another gate, the velocity gate, and that is to say that also the return angle of the electron depends on the relative phase of the two colors. And if you think about that in a bit more detail, you actually find that this determines the ratio of even to odd harmonics. And that's another observable, that's a second observable you can measure. And that's how then the experimental result really looks like. In the upper part, you have the measurement of the two observables. So vertical axis is harmonic order. Horizontal axis is the relative delay between omega and 2 omega. And the color in the left panel shows you the harmonic strength, the signal, and the color in the right panel shows you the ratio of even to odd harmonics. If you use these two observables to reconstruct ionization and return time, you find the results in the bottom panel. The red dots are the experimental results, and they are compared here with the gray line, which is the classical Simpleman's model. And you see it does not really fit well to that, but the measurement matches very well the black line, which is the quantum orbit, the SFA times from the saddle point equations. So since we will be using this scheme later on, I think it's good to look once at the equations that you need to solve. So as I said, you have these two gates, and for each of these two gates you have an equation. So the first gate is the displacement gate, and what really happens is that if you want the electron to return to the parent ion in the presence of the two-color field, then because it's a curved trajectory, you will need a certain initial transverse velocity. Initial transverse velocity to make it return. And just from classical arguments, you find this equation here, which depends on Ti, Tr, and the relative phase phi. And you expect that you get the maximum signal if this transverse velocity is 0, which happens for a certain choice of phase. And then there's the velocity gate, which tells you what is the angle of the returning electron. And if you want to maximize that, you have to set the derivative of this classical expression to 0. And that gives you then two equations to retrieve the two times. But actually in our implementation, we find that it's better to use these equations with complex times. So Ti and Tr are now complex, which then actually means that it's really 4 equations. And if we have 2 observables and 4 equations, we need to make some extra assumptions, but that's not a big problem. We set the imaginary part of the return time to 0 because we know it's small. And one other assumption that we make is that we set the imaginary part of the ionization time to the Keldysh time, which is a simple formula that we can just plug in. And if we do that, we can actually go and reproduce the experiment. So what we have done already many years ago is solve the 2D or 3D numerical time-dependent Schrödinger equation for a helium atom with these parameters. And in the right, you see the traces for the harmonic signal and a y to x amplitude ratio. It looks very much like in the experiment. And then we do this timed retrieval, and then you find the result on the left. So again, harmonic order is plotted on the vertical axis, and on the horizontal axis is time. And we show here both ionization time and return time. You should look here at basically the purple points, which agree very well with the quantum orbit model, which is the thick gray line in the background. You can't see it because actually the TDSE result overlaps with the quantum orbit result. So two things. One thing is important. I should emphasize that the point here is that you can measure or determine ionization time and return time for every harmonic order separately. And now there is one striking result here. These retrieved times are amazingly close to the quantum orbit times. And I remember that probably 5 years ago when I gave a talk and I included this result, Dieter, who is our chairman now, actually asked me this question: why is this result so close to the quantum orbit model? Are there no Coulomb effects? Actually, at the time, I couldn't give a good answer, but I can give the answer now. So before I do that, I want to remind you why we actually would expect to see some shifts, some difference between these results. And to that end, let's think about the Otto clock. The Otto clock has been introduced by some other speakers already. So there we observe photoelectrons from ionization in a strong field. And that's usually a near circularly polarized pulse, so that your momentum distribution is like a torus. And then we can determine the angle under which the maximum signal is observed. And that angle has to do something with the ionization time. And we know that there is a strong Coulomb effect on the outgoing electron that will modify this angle, as we see in this picture that I have stolen, like all the other speakers, from the paper by Torlina et al. So putting this the other way, it means that if you look at a fixed momentum, then for this given momentum, the ionization time is changed by the Coulomb potential. It's not the same as in the short range potential. So in the same way, we would expect that to happen for the harmonic generation. So, okay, the question is, can we use something like the Atto-clock principle to learn something about the ionization time in high harmonic generation? And that's, of course, difficult because the setting is different. We have circular polarization in one case, linear polarization in the other case. And one could think about doing the Atto-clock with linear polarization, but it's just not possible because in linear polarization, you have a lot of effects. You have intracycle, subcycle interference, you have rescattering, you have Coulomb focusing, holography, all that into one distribution. So it's very complicated and you cannot analyze it like an Atto-clock. But there's a trick. We can use a bicircular field. So in particular, we can use a superposition of two counter-rotating fields with frequency omega and 2 omega. Depending on the ratio of field strength, the total field shape will look like one of these pictures. And we are particularly interested in this 2-to-1 ratio, because what does it do? It actually it features 3 times per optical cycle indicated by the red circles, where the total field of this bicircular field mimics linear polarization. So if you look here, as we approach this endpoint here, the electric field basically moves on a line. So we can actually use this bicircular field to learn something about the ionization mechanism in linearly polarized light. And that's what we do in the following. So this shows you some results of our calculations. On the left, you see then photoelectron momentum distribution created by such a 2-to-1 bicircular field. The left one is calculated using SFA with a CW field, and that's why the 3 blobs in this threefold structure are equally strong. In the right picture, you see the result from a TDSE calculation for a short pulse, and there we prefer one of these 3 lobes because of the short pulse length, and this is the one that we analyze in the following. The important finding here is that you see that when you project this distribution on the vertical axis, it's not symmetric, it's not up and down symmetric around 0, but there's an upshift here. And this is exactly analogous to the Atto-clock angle in the circular polarization. So we will analyze this Atto-clock shift in the following, but there is one, maybe now I should emphasize there is one limitation of this Atto-clock principle, because of course it gives you only one ionization time. I mean, if you have a model in how that helps you to analyze this result, what you basically do is you look at the location of the peak and you assign an ionization time to that peak. You cannot do a momentum resolved measurement of ionization time. In order to do that, you would have to do something additional, and that's what we have also done. You could combine this, this ionizing field with the weak probe field. That's what we now call the 2-color method combined with the bicircular field. So for example, look at this picture here. In addition to the ionizing field in red, we apply this 2 omega streaking field pointing perpendicular to the ionizing field. And here on the right is a picture for parallel polarization. So it's a little bit complicated to think about the details of this scheme. So I just try to explain it in very few terms. What you have to do is you have to pick a momentum in the momentum plane. So you go somewhere and then you watch the strength of the photoelectron signal as a function of the relative phase between the ionizing field and the probe field. And from this optimal phase, where the signal is maximized, you can calculate back to what the ionization time must have been. And that actually works with very simple equations here on the left and here on the right for the two different polarization cases. So this retrieval of the time is actually much simpler than in the high harmonic generation case. And now let's see what is the result that we get for a helium atom ionized with this 2-to-1 bicircular field. So this is basically the typical plot that you always see when you analyze the Otto clock. In the Otto clock, you have on the vertical axis the Otto clock angle, and on the right axis, on the horizontal axis, the laser intensity. So here in the the vertical axis is the relative upward shift that I showed you before, which is analogous to the Otto clock angle. The black dots is the shift itself. So like we are used to from the Otto clock, this decays, it decreases a little bit with intensity. And the other two, the blue and the red dots, are the results from the two-color probing method. Now we see something very interesting. If we use the orthogonal probing, where the 2-omega field is perpendicular to the ionizing field, we see that it's basically useless. You see that I should explain in a bit more detail what's shown here. The red curve and the blue curve are those momenta that correspond to ionization at time 0. That means at the peak of the applied laser field. So you see that the blue curve does not agree at all with the Otto clock shift. But in the red case, where we do the parallel probing, we have very good agreement. So the agreement between the red and the black actually tells us that the maximum signal corresponds to ionization at the peak of the field. So this means that the orthogonal probing actually cannot measure the Coulomb shift of the ionization time, but the parallel can measure it. And now what is the reason for this? And this is now actually coming back to the problem in high harmonic generation. Actually, the time retrieval equations that we have used here and also in the high harmonic generation case, like they were developed by Dudovic and co-workers, they do not include the Coulomb field. So the assumption is basically that the motion due to the probe field shows no Coulomb effects. And that is, of course, maybe not quite correct. And it's an approximation. And now what it turns out that actually if you have omega 2 omega, then you have Coulomb effects both in the omega direction and in the 2 omega directions, and these just cancel each other in such a way that the atom essentially behaves as if it had a short range potential. This does not happen in the parallel case. Okay, now I will make this here very brief. We have applied this bicircular Otto clock also to molecules, and we found something interesting there. So we did it for a simple helium H+ molecule that is either aligned along the ionizing field or in the opposite direction, two different cases. And the interesting thing is that we do see an Otto clock shift, of course, as with an atom. And this Otto clock shift is orientation dependent. It depends on how we place the molecule, but the ionization time is not orientation dependent. No matter whether the molecule points up or down, ionization is always most strong when at the time of the peak field strength. I will also not go into much detail about the non-dipole effects. I just want to mention maybe one thing here. This is something that we have also published in connection with the bicircular Otto clock. You could actually use, instead of the 2 omega field polarized perpendicular to the ionizing field, you could instead exploit the Lorentz force on the outgoing electron due to the magnetic field, because that Lorentz force also is in the perpendicular direction. It's actually in the propagation direction of your laser field. So you could think of replacing the 2 omega probe by that Lorentz force. And we have analyzed that, and we found that actually this kind of Otto clock also does not give you the true ionization time. It also kind of measures the Coulomb free time. So what that really means is, if you look at the result, that whereas your distribution shows an autoclock shift, as we see in the top here, the position where your forward non-dipole shift that comes from the radiation pressure is minimal always remains in the center of this distribution. It does not follow the autoclock shift. Okay, but let me come back in the final few minutes to the high harmonic generation case. So the question is, can we make this orthogonal probing work nevertheless? So we found something interesting there. We actually repeated this probing, not using 2 omega fields, but other streaking frequencies. So here you see results where we always ionize, or where we always generate harmonics with the same fundamental frequency, which is 800 nanometers in this case. But the probe field, which is in the perpendicular direction, is varied from 1.4 omega to 4.6 omega. And the interesting finding is that if you look at this result plot where we have harmonic order on the vertical axis, ionization time on the horizontal, we see that all the low frequency streaking frequencies give rise to the results in the right part here, whereas all the high frequencies give results in the left part. So there's an obvious difference between high frequency and low frequency probe fields or streaking fields. And now I think it's time to really look at the question, how do we actually expect the Coulomb potential to affect this ionization time? So we have the quantum orbit times from SFA, and the question is, how are they changed by the presence of the Coulomb potential? I show you 3 different ways to address this problem. One is probably well known to many of you. It's called the analytical R matrix theory, developed by Olga Smirnova and her co-workers. There, you correct the SFA action by adding a Coulomb term, which is essentially the time integral of the Coulomb potential. And then what you can do is you can find the corrected saddle point times by calculating the new saddle points. I'll show you the results in a minute. An alternative model that we have set up is a classical model. We call it here a modified classical model. It uses Newtonian trajectories in the presence of the Coulomb potential and the external field. It uses a little bit of SFA input for the starting conditions, and we use 0 transverse velocity. And from that, we can then derive numerically a new relation between the ionization time and the harmonic order. And the last one is the simplest one, and let me explain that briefly. In the autoclock, or in general, if you ionize with a low frequency field, there's actually a very simple way to estimate the Coulomb effect on the outgoing electron. In the adiabatic limit, so for a slowly varying field, Nikolai Shvetsov-Shchilovsky has actually derived many years ago this simple formula. That's the momentum kick on the escaping electron in the presence of the Coulomb field. It's proportional to the electric
I think we may have lost Manfred's connection.
Yes, I was wondering whether it's just me who doesn't hear him.
No, I think he's dropped off, unfortunately.
So should we wait whether he resumes or just continue?
Contact him by Slack and let him know he has dropped. Maybe he doesn't know.
Probably he will not read it during his talk. Okay, but there's no other way to continue now with the next speaker, right? I also see no questions so far. So if you have questions to Manfred, please post them in the Slack workspace. So the next speaker is Stefanie Gräfe from Jena, and she will talk about the impact of electron-electron correlation in ultra-fast attosecond single ionization dynamics. Stefanie, you are muted.
Thank you. So sorry for that. Thank you, Carla and her team, for making a rearrangement of this meeting from real space into virtual space. That was really a wonderful experience here. And thank you also for the invitation to talk here. My talk is entitled more on the attosecond part, while the previous ones were more on the strong field part. So the focus of my talk will be on the impact of electron-electron correlation in ultra-fast attosecond single ionization dynamics. And would like to, in the beginning, acknowledge the team, so the PhD students working on that and the postdoc working on that. So I'll start with a short, freshing up. So what happens in single photon, single ionization? Let's assume we have some kind of an atom atomic potential here. You're on the ground state. You have some energy which you need to overcome, so the ionization potential. And let's say the field of the XUV pulse is high enough such that the frequency is higher than what you would need to overcome IP. You would directly ionize, and the rest of the energy difference will go into kinetic energy of photoelectrons. Okay, so you can more or less treat it perturbatively, and if you now look for such a hydrogen-like atom, we ionize by an 80 nanometer XUV pulse, and what we change here on this slide here is the pulse length. So this is a photoelectron spectrum, and we start with a blue curve, something like that. We have a blue spectrum here. It's more or less centered around a certain frequency, which corresponds to that one. Now what you do is you decrease the pulse length, so we get shorter and shorter, so from 10 going towards attosecond pulses. So what happens, the first thing you see is the amplitude decreases, but if you zoom in this region down here, you see also this, the spectrum shifts towards much smaller energies. So what happens here is also more or less understandable by perturbation theory, as I said already, because if you think about the spectrum, you can see that it consists of two parts, one part being dominated by the transition dipole moment, the K dependence here, and the spectrum of the field. And if you look at this for the case of the 10 femtosecond field, the blue curve is now what is the spectral width of the field, and the orange one is the transition dipole from this ground state to continuum states, in assumption here a plane wave. And you compare now what is perturbation theory and the Schrödinger equation will tell you, see that it more or less coincides perfectly. Now you make the pulse shorter and shorter. So if you go shorter, now we have 1 femtosecond pulse. The first thing, of course, the pulse gets broader. Transition dipole, of course, doesn't change. And if you now overlap, then you have the product of this part, the blue part and the orange part. So you see here, still dominated by here the spectrum here. So this is a photoelectron spectrum here. Again, perturbation theory and Schrödinger equation match perfectly. Now pulses get even shorter. We're coming to attosecond domain, so 560 attosecond. Now pulses get even broader, and you see it starts to shift because now the overlap here, the dipole moment gets very much, or like very fades off quickly to 0. So the spectrum overall shifts to much smaller energies. And this is even more pronounced if the pulse gets shorter, so the spectrum even broader, then it's more or less really dominated by the region here at very small energies. So the overall spectrum shifts to smaller energies, here mainly dominated by the contribution of the transition dipole moment. So what I've shown here is something like a warm up. You know, it's for a single atom, no correlation, 1 electron. So if you look further, I would like to come more to this, what we talked about, many electron. This is one of the papers, which is very, very famous, a group of Mark Schulzer and the theory from Burgdorfer's group, which is called attosecond correlation dynamics. Now the system is not the hydrogen atom anymore, but the helium atom. And if you look at the helium atom, what you have here, and when you ionize by a single attosecond pulse, you have different processes. You have single ionization, but you have also something like shakedown and different shake-up processes. So there are different other processes occurring in the case of 2 electron systems. So the question, which is more or less related to the talk, is if you have now attosecond single ionization in systems where you have correlated electronic dynamics, you of course leave the single electron picture. So you have some different processes. You have shake up, knock up, shake down, knock down processes, and delayed ionizations. We get here all the time chat windows which are hiding afterwards. I cannot see it currently. So and of course Auger processes. What you also realize that most of the work is really for atomic systems and not so much about molecular systems. And this is where I would like to drop in today and introduce something about a molecular model system here. The first thing I would like to introduce this model system, it's maybe a little bit unusual. It's shown here. It is already known for quite some time. It has been suggested by Horia Meteo and Shin, and afterwards also extended by Volker Engel and co-workers. So let's imagine the following. You have 2 nuclei, 2 protons which are fixed in space. So it's not like H3+, which can fit. You have 2 protons which are fixed in space on the left and on the right-hand side. And in the middle, there is 1 proton which can move in between these 2 nuclei. Additionally, you have 2 electrons which can move, and we have 1 electron X and an electron Y in the following. So you have 3 particles which can move. What we do is we have reduced dimensionality, so we collapse onto 1D. So we force restriction in 1D. So how does the Hamiltonian look like? You have the kinetic part of the nuclei, you have the kinetic part of 1 electron, the X electron, and the kinetic part of the second electron. Sorry, there's 1 minus too much here, sorry. The kinetic part of the second electron, and you have the potential. And the potential is a bit more demanding. So you have, if you focus on that, this potential, you have 2 parts, or different parts. You have the Coulomb repulsion between the moving nucleus and this nucleus, so nuclear repulsion. You have a term which is interaction of electron Y with all of the nuclei, so with the left one, with the right one, and with the moving one. These are these 3 terms. And we have interaction of this second electron, the X electron, with all 3 nuclei, plus an additional term, electron-electron interaction. So we do that, we have potential. So I would like to focus that we take here error functions in order to have some kind of screen Coulomb interaction. And with these parameters here, which are shown here, you can screen the interaction strengths. At the moment, we will not change it, so these things are kept fixed. So if you do this, you can assume to use Born-Oppenheimer approximation. So let's say we fix the nucleus in different position and calculate eigenstates, electronic eigenstates. And this is what is shown here. So this is now as a function of nuclear coordinates, so 2 nucleus fixed, and the second one is, or this moving nucleus is fixed at different positions, and we looked at the electronic eigenstates. The lower part here is now the 2 electron states, and this is what I would like to call the cationic states, so where 1 electron has been ionized. So we have here many electronic eigenstates of the cation. The pulse which we use to ionize here is an XUV pulse with a pulse length of 18 nanometers. So in other scales, 15.5 electron volts or 0.57 atomic units. And we start here at 1 of this minima, so at around -2 angstrom, where the nucleus is fixed. Yeah, so you can see we have 2 minima, 1 when it's more to the left and 1 when the nucleus is more to the right. So they are absolutely symmetric, of course, there's no preference. We start from this one particular position. And we ionize with this 15.5 electron volt, so it's approximately where this arrow comes in. We can easily ionize, singly ionize, but with this very large spectral width, as we discussed in the beginning, we have a pulse length of 140 attoseconds. The spectral width is something like 18.4 electron volts, or in other words, 0.6 atomic units. So it's really broad, as it's schematically shown here by this red to blue transition here. So we can cover ionization into different electronic states. Okay, so now we have sent where the nucleus is now fixed on a position which is on negative values here. And now the question is, where are the electrons sitting? So if you now look for one particular situation, namely nucleus sitting at -2 angstroms, so here in this minimum here, we look now, where are the electrons sitting? And this is now a plot from the two-electron wave function. Here it's coordinate x, here's coordinate y. So nucleus at 2, and if you look here, this is the ground state. You can see here we have one blob here, which corresponds to x electron being at negative value, while at the same time the y electron being at positive value. So similar like it's shown here. And of course, because it's indistinguishable, you have the same here, x electron at positive values and the y electron at negative values. So indistinguishability. Still, if you look a bit closer, if you say the nucleus is on the left-hand side, this electron, which I call now x, the left electron is between two closer sitting nuclei, so it's stronger bound. And this one here is where the nucleus are a little bit further away, so it's a little bit weaker bound. So ionization of this one and this one will be not the same. Good. Still, they're indistinguishable. We don't know which one is X, which one is Y. Now, this is now the ground state. We know where the nucleus is sitting. We know where the electrons now are sitting. And now we come to interaction with this very short attosecond pulse. As I said, it's 80 nanometers wavelengths. And what we look here is now a snapshot at electron density. So we propagate a Schrödinger equation for 3 particles in 1D. And here is a snapshot of the electron density 3 femtoseconds after interaction with this XUV pulse, with this attosecond pulse. So on this axis is where the one electron is, second coordinate of second electron. And first thing you see is like that something is running out along here the axis. So if you look at what happens along this axis, it is around where X is at very small coordinates, so X remains, while Y electron is moving along this axis. So this would be moving out in positive values, Y electron moving out at negative values. So Y leaving, X remaining, so single ionization channel. The same also for this channel here, now just opposite. Now we have here, like in the box, the Y electron stays at values around 0, so in the system, while the X electron is moving out in left or in the right direction. The next part which you see here is not much going out here, where both X and Y would be large. This would correspond to double ionization. Would like to stress it's a log scale, so it's not much coming out here. In the analysis which I present today, we will not focus on these parts here. The part which stays at small x and small y, so this part here mainly in the middle, this is what remains bound. So we have a major part which is not ionized, so it stays neutral. Also this part I will not focus on today. The second part is another part which is also shown here. You have here this kind of diagonal, and this is mirror symmetric again because x and y are indistinguishable. So in principle, if you can pay the mirror symmetry, it's enough to analyze one of these channels, because for the other thing, mirror symmetry applies. So in the following, I will focus on this particular channel. Again, this one will be the same because of mirror symmetry. So let's look now here in this particular part. Good. So I zoom in here a little bit. So what this means here on the left, we have one part X electron leaving, Y electron remaining. You see here some kind of a double stripe structure. So something where Y electron stays at positive values, and here something where Y electron is afterwards at negative values. So a double stripe in each of the direction. The second part, you also see that backwards and forward ionization channels, so electron flying to this side or electron flying to this side, is also not symmetric. And this looks like So electron here is moving. It looks like we have here several channels, so right or left. And it looks like there are different pathways contributing to ionization. Yeah, so in the following, I will really mark these channels by forward, so meaning electron going to the right, and backward electron here going to negative value to the left. And I will use also the label up and down, up when electron Y stays at positive values, so where it's here, and down when electron Y is at negative value. And now the following, I would like to analyze a few of these pathways. Good. So first thing, we check, now this is the interaction with this field. It's quite intense. It's about 10 to the 15 watts per square centimeters. And what happens to the remaining electron, you see that there are also like several electronic states. So the color code is the same as here. The ground state is violet. The first excited state in the cation is green. And so on. You can see that there are many electronic states being populated, not only electronic ground state. Another indication that there are several channels involved. Now, let's look on these channels. This is what we have seen before. This is backward and this is forward, up and down. X electron is leaving, as I said, and now we look what is with the Y electron. And we look in each of the channels as a function of time, what happens with the Y electron. So we look here at the momentum. So momentum expectation value of the Y electron. So what you can see there, I mean, up left corner and here down right corner, the Y electron is almost not moving, maybe a little bit oscillating, but there are two parts, so forward up and backward down, when you see strong oscillation. So meaning the Y electron is really oscillating forth and back. And this is what we will look now a little bit in detail. I would like to stress here that these things are still indistinguishable. So we don't know whether it's X or Y, we just know one is leaving and one is remaining, and the remaining one can be either sitting still or oscillating. Good. So let's focus first on electron flying to the right, so the forward channel. And now we distinguish what happens here in the up or in the down region. So down, we now say like down, nothing happens here. So this means electron X is going to the right. This one here, nothing happens. So this is more or less a direct emission, while forward up, so electron, the second electron here is being oscillating. It's kind of an indirect emission or something where at least collision or something was involved. And the same if you look now on the back side, so electron moving to the left, so to negative values. Also here we have one part which is more or less direct emission, and one when you see really strong oscillation of the remaining electron, which indicates that there's some electronic dynamics involved here. Good. Again, we're indistinguishable, we don't know. So what we do now in the following, we artificially distinguish electrons. So we do the following. This is the plot we have seen in the beginning. This is the ground state electronic wave function. And now we make artificial subsystems. So we switch off correlation in a time. So let's say we make a cut. We take only that part of the wave function and call this subsystem A. So meaning now if we take this blob here, the electron X is at negative value and electron Y is at positive value. So we can label them now X and Y. They are not indistinguishable anymore, but distinguishable. And on the other hand, we make a second artificial subsystem. Let's call it B. This is now the second blob of the full wave function when the X electron is now at positive value and the Y electron at negative value. So the label would be vice versa. So if we take subsystem A, so X electron negative, Y electron positive, it's exactly like it's shown here. Then this means the X electron is the stronger bound one and the Y electron is a little bit weaker bound. So we distinguish. Now we do the same, what we looked now in this ionization dynamics, we do now the same for the full system and the subsystems here. So this is the plot you have seen, and I will zoom now a little bit in this region here, when the electron has left the system and moving outward, and we look at this at a function of time. This is now the full system. Again, X electron leaving, Y electron remains. You see in the backward direction, there's almost at the same time two stripes occurring, so Y electron at positive values and Y electron at negative values, while in the forward direction you see some very strong channel down here and only much weaker channel up here occurring also a little bit later. So again, as we cannot distinguish electron, we now use this artificial subsets. So, and this is what I will now show here. This is now subset A. I will say a little bit of what comes later. Just look from optical inspection, you see the right side, so the forward channel is very, very much different, while the backward side, so the left parts, is more or less similar. So the backward part can more or less be described by subsystem A with some additional features, which I will say later. While here, this is what subsystem B is doing. You can see by optical inspection that here the forward part matches much better to the full system, and this part is not so well described. Yeah. So here, forward dominated by subsystem B, and here the backward part more by subsystem A. If you didn't memorize what is A and B, doesn't matter. This is what we will do now a little bit more detail. So we come now part B. So just here, this part, we look now in this channel here, these parts, where we said it looks very much similar. We focus on this dynamics here. So electron moving out of subsystem B. It takes a subsystem because now we can distinguish electron and distinguish which channels is here. So B had the following definition. The X electron is positive. The Y electron is at negative values. The X electron is weaker bound because it has a larger distance here. And the Y electron is stronger bound. So we're distinguishable. And again, because we look only along the horizontal axis, we know always it's X leaving. So this guy here. So this guy is leaving, and we look at the positive part. We look at X electron moving towards positive coordinate values. So this part, exactly the plot what you have seen on the previous slide. So we'd say X electron is leaving, yeah, and now we look what is with the Y electron. We said we have two channels here, an upper one and a lower one, and these were the two momenta of this remaining electron. And now maybe we should first concentrate on the lower channel. So lower channel meaning Y electron at negative values. This means simply X electron moves away and the Y electron stays absolutely where it was. Nothing happens. So it's almost not affected by the weak electron, the weaker bound electron moving out. And this is exactly what you can see here. Almost no momentum, the electron just remains, almost unaffected. So this is a direct emission, and this will be also the dominant contribution. The second part, we have another channel. This would be here the violet one, when afterwards the Y electron is at positive values. So it means it must have afterwards moved here. And afterwards moved here is exactly what you see here. It has some dynamics moving, electron dynamics moving, so a creation of an electronic wave packet. So meaning we are not in the ground state anymore, but we had some electronic dynamics. We had really created here an electronic wave packet. So we involve several excited electronic states. So, and this is what we would call a knock-up process. So the electron coming from the ground state is now knocked up to excited different electronic states. This is what we can see by this artificial distinguishing these electrons. This was for the forward direction, and now we can do the same for the backward direction. So in the backward direction, now this one is the X electron. Again, we take now the other subsystem and here, and this is the X electron is a stronger bound being at negative value. And now for this subsystem, the Y electron is the weaker bound sitting at positive values. Again, we look at dynamics where X is ejected. And in this part, we look now in the part where electron X is moving out to negative values. So this part here of the dynamics. So, and again, we have also here two different channels. So the electron moving out here at negative values. And we have one part where Y electron is positive and one part where Y electron is negative. We do the same analysis here. So this was the two different momenta for up and down channel of this remaining electron. And what we can see here, if we take now, we look at this violet box here, the more dominant channel. The dominant channel is meaning if X electron moves to the left, so as is shown here in the picture, the Y electron stays on this side at positive values. So, and this is this part here. It's almost unaffected. It's a little bit affected because of the following reason. It's a weaker bound electron. And if the strong one leaves the system, of course, there's a little bit of readjustment here, but it's more or less a direct channel, so this one is not affected. However, the electron being the weaker bound is not the electronic ground state, so we inevitably end up in an excited electronic state of the cation. Second, so it's a direct emission. Second part, we look now at the green box here, when the Y electron has moved obviously to the left part, so to negative coordinate values. And now this corresponds to more going to a ground state, so from an excited state to a ground state. And this oscillation here is a really regular oscillation, which you can see here. If you make a Fourier transform, you can really directly relate it to two different electronic states. And this would be a knockdown process. Yeah. So by this analysis, you can really analyze which pathway is contributing to which electronic state, to which dynamics does it lead, and what is the dynamics of the remaining system. Good. With this, I'm almost in the end. So what you can do afterwards, I will not do this for time reasons. You can look now at the population of the cation in forward and backward direction and address it to different aspects. So here is mainly in the ground state. So more or less the direct emission, you can analyze by the different pathways. And here it's a mixture of different different excited states contributing. So here's the direct emission, and here we have knock up, knock down, different other processes in the different direction. The second part, which I will shortly mention, is that there's also some post-ionization dynamics, because if you end up here in an excited state with your wave packet, you have vibrational dynamics involved, and you end up here in some kind of a conical intersection. And in 1D, it's of course only a curve crossing, a non-adiabatic curve crossing. So there's also non-adiabatic dynamics afterwards in the cation, which I will not talk about much today, but this of course also can happen, however, on much different time scales. So with this, I would come to the summary. So what I've shown you was a single photon, single ionization in a simple molecular model system, and that we can analyze different pathways leading to ionization. And by making artificial subsystems with distinguishable electrons, we can discriminate different pathways. We can understand direct emission, knock up, knock down, and many other processes more, which I did not focus because of time. We could see a creation of electronic wave packets in the cation and relaxation, and contributions of both for the expert static and dynamic electron correlation, and afterwards triggering vibrational dynamics in the cation. So what we will do next, I mean, the idea is now to see how we can understand this in the photoelectron spectra, and I show you one of the plots we have. So the spectra in forward and backward direction looks similar, but it's extremely hard to understand and analyze because there's a lot of electronic structure, vibrational structure, and also, let's say, probably some numerics, which is not accurate enough here. And also what we would like to see is what we now switched off was, of course, correlation. And to distinguish electrons does not mean that we treat electron correlation. So we would like to test it with different approaches, like time-dependent Hartree-Fock, for example, to really distinguish which part is correlation-driven and which part is just because of indistinguishability. And of course, the idea would be afterwards to apply this to real molecules. So I would like to acknowledge my group, but in particular these two guys, so the postdoc Alexander Schubert and Michael Ziems, the PhD student who do that, who did a lot of work on that, and the money. And thank you very much for your attention.
Yeah, thank you, Stephanie, for this nice talk. So are there questions? Yes, there is one by Daria Gorilova. Please ask your question.
Yes, so I'm trying to unmute. Can you hear me now?
Yes.
Yeah, great. So thank you for your nice and very illustrative talk. So I have a questions to these distinguishable subsystems. So maybe from a bit from theoretical or quantum mechanical point of view. So maybe it would be easier to say, or to say that you project on a certain basis states. So maybe like, because we are used in a quantum mechanics, so that we can project some certain states on some other states, or so on eigenstates, or we can project on basis states. So, and then it would be more precise, something what we are more used to. So my question, so have you considered to view it in this way?
Thank you very much. It's of course a reasonable question, very much. So the problem is the following: you have, because the spectral width of the pulse is so broad, if you try to project out all other states not contributing from the neutral, we projected up to states 300 and still some small contributions of smaller parts being left. So it became really not beautiful to really make it an unambiguous statement. Now we have no neutral anymore, but only cationic states. So this didn't work. It's an infinite series, of course, of bound states. So this didn't work too well.
So there's another question by Emilio Pisanti, please.
So some of the wave packet plots you showed with momentum have oscillations, and then the oscillations die out. Is that due to decoherence, due to nuclear motion getting involved, or is that just the wave packet becoming complicated?
Some part of nuclear motion, I didn't focus on that, and I, from time reason, will not go back. There was, we did, of course, the same by freezing the nuclear dynamics, and there was some small difference related to like decoherence, let's say, due to nuclear part, but the rest is just purely dephasing because of contribution of different electronic states.
Okay, cool, thanks.
Okay, I don't see further questions. So now Manfred has the chance to wrap up his talk. He was...
There was a hand raised by Hardy Gross. Yeah.
Sorry.
I have a question myself. How about spin? So electronic correlation should be very different when you have two upspins, or one spin down, one spin up.
Absolutely. So this is exactly what we're currently doing. So a perfect question. Also, if you have two electrons, and I mean the total wave function must be antisymmetric. So you can either do it by having symmetric in space and antisymmetric in spin, or vice versa. And now we're exactly looking at that part, how this different things would impact ionization. The original hope was to look at this at double ionization, but the signal, as you have seen, is very weak. So we played with the wavelengths, but still double ionization, the direct transition is very, very weak. And yeah, I hope to have it in the double ionization signal. It's, at the moment, I would say that numerics is not trustable, but in single ionization, this is exactly what we're doing now as well. I can't say what happens.
Okay, I hope I don't miss further questions. Okay, then Manfred, can you finish in 5 minutes or so at the latest, because the battle starts soon, right?
Yes, I'm trying. Okay. I think I got thrown out exactly at this point. So now you can hear me and see me and see the screen?
Yes.
Okay, very good. Okay, I will do it quickly. So I showed you the three models to model the Coulomb shift of the ionization time in high harmonic generation. And as we see here, this is the result of the three models. They are very similar to each other. And they differ from the quantum orbit time, which is the gray line, and also very much from the Simpleman's model, which is the dashed line. Okay, and now let's see how the retrieve times look that we get from the TDSE two-color scheme. So on the vertical axis now we have the ionization time, and I plot here the results for 4 different harmonic orders: 42, 47, 50, 53. And the black dot dash is the quantum orbit times without Coulomb, and then the red and violet are the models for the Coulomb shifted ionization time. And this is the result from the two-color harmonic generation at various frequencies. And so you see there's a very interesting double plateau structure. At low frequency, this scheme yields the Coulomb free time. At high frequency, it yields something that is actually quite close to the models for the Coulomb shifted time. So the finding is that, or the explanation is that at low frequency, we somehow have the problem that we cannot neglect the Coulomb effect in this time retrieval equations, and therefore we, when we do it nevertheless, we measure the Coulomb free time. And in the high frequency, the scheme is adequate. So we measure the correct ionization time. So a proposal for an experiment would be, for example, do the measurement for omega-2 omega and another one for omega-4 omega, look at the difference, and that should give you the Coulomb shift of the ionization time. Okay, and that was my conclusions slide. I showed you in the beginning the 2-to-1 bicircular Atto clock. I hope I could convince you that it's a very interesting and nice tool to measure aspects of ionization with maybe higher accuracy as the other fields that we are used to. And then in the second part, I showed you in the last part, I showed you results from this 2-color orthogonal high harmonic generation, where we see this interesting difference between low frequency probing and high frequency probing. And hoping that I was not cut off this time, I would like to conclude and thank you for your attention.
Yeah, thank you, Manfred. You were not cut off. So are there questions to Manfred? We don't see raised hands. So I have one question. You had this plot with the ionization times and then high frequency and low frequency, and they came in groups. So why is this transition not continuous from high to low frequency?
Well, okay, I think you are referring to this plot. Is that right?
I cannot see anymore because you don't share the screen.
Okay, I'm sorry. I will do it quickly. Now you should see it.
Yes.
Okay, I think this is the plot you are referring to.
Yes.
It looks as if there's no transition, but if you look at the last plots that I showed just now, this is basically the same thing, just plotted in a different way. So here we really, we do it for many, many different streaking frequencies, and we see that there is a continuous transition. But there is a kind of double plateau structure. So in what I've shown you in the other plot were points that were either in the low frequency plateau or in the high frequency plateau that you see here.
Okay. Good. So are there other questions? I don't see raised hands or questions in the Q&A box. So then I would like to thank all speakers and the organizers for assisting me. Are there announcements by the organizers? Seems not the case. So then I would like to thank you all, and then I close this session. Bye.